Yep. All right, so let's take a look at what was the change in kinetic energy. Ultimately, the total work, this is the work-energy relationship, is equal to the change in kinetic energy. W here stands for work, not weight, and it's a bad habit I get into of using capital W for weight, but W here for work, capital K for kinetic energy. Now the work we already figured out. That was what we did in another presentation. So the total work done is 0.0669 joules. So let's figure out what the kinetic energy is. I know the change, that's going to be equal to the final kinetic minus the initial kinetic, because change is always final minus initial. Kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. Now, the initial velocity was 0. I started that thing at rest, and then I let go, was timing. So that term right there is going to be 0. So that makes that a little bit more convenient. It simplifies things. And so what I need to figure out, though, I know the mass, and recognize that's the mass of both things. I got two masses here. Both are moving. Both have kinetic energy. So I have to take both into account. I could break this up into kinetic energy of 1 and 2, but in essence, both masses were moving at the same velocity. That's the whole point of the tension and that whole bit. Both masses moving at the same velocity at any particular point in time. And so my mass here is 1/2 times, well, it was a 200 gram mass and a 210 gram mass, combined mass. And so the total mass that was moving was 410 grams. So this should be 0.410 kilograms times my velocity at the end, just before it hit the platform or it hit the top. So when I'm trying to figure out velocity, I have to think, all right, how do I figure this out? I know the initial velocity. I don't know the acceleration because it's not in free fall. It's not 9.8 meters per second squared. It's not the acceleration of this object falling. So I need to figure out what it is. Now I do have a clue though. I am working under the assumption that acceleration is constant, that we have a set number of forces acting on it, and the magnitude of the force does not change. And so therefore, if the force is constant, acceleration is constant. If acceleration is constant, well, then I know my average velocity is just the average of my initial and final. So let's go through that math just real quick here. I know my average velocity is just going to be my initial velocity plus my final velocity divided by 2. That's if acceleration is constant. I also know average velocity is going to be my change in displacement over change in time. If only I knew what my change in displacement was. I do. That's what we did over here. And so that should be equal to 0.683 meters divided by the amount of time it took. 2.697 seconds. Pull out the calculator. And so 0.683, enter, 2.697 divided by, and I get 0.253 meters per second. So about a 1/4 meter per second. That's my average. That's how fast it was going. If my two masses were doing this right here, that was the speed in the middle, actually. And so, yeah. Wait, I'm going to have to think about that one a little bit longer. Well, definitely middle time. Not necessarily middle of the location. So I've got, that's my average right there. That's going to be equal to my initial plus final divided by 2, but my initial is 0. So that is just half of my final velocity in, well, speed. And so I take that number, I multiply by 2, and so my final velocity My final speed, I keep using the word velocity. They each have velocities in opposite direction, but we're dealing with kinetic energy. Kinetic energy is 1/2 mv squared. That v right there, you can treat it like a dot product with the velocity vector, or just times speed times just the speed. Direction doesn't matter with energy here. So my final speed is 0.506 meters per second. So I stick that one up here. So 0.506 meters per second squared. I crank through that, and let's see what we end up with here. So let's see, I square, nope, wrong button. There we go. I square that right there. 0.41 times 2 divided by, and what I end up with is 0.05226 joules. Now, the amount of work that I calculated that we did was 0.0669 joules. The amount of kinetic energy, change in kinetic energy is 0.0526 joules. Let's figure out what the percent difference is. One is not necessarily better than the other because friction is messing this thing up. And so we end up with, let's see, I want to do difference divided by the average. And so my percent difference is 24% off. I've seen worse results, but that is the experiment. Now, the question is, can we get better results? Well, here's the trade-off. When doing this experiment, if I have less mass differential, so the amount of work total work that's being done is smaller, then the friction becomes a more significant piece of it. And so, therefore, having a greater mass difference there between the two masses, so maybe I did 500 grams and 200 grams, friction is not going to be as significant. However, the timing becomes off because it becomes a lot harder to do the timing. And so there is an optimum in order to actually show this, but reality is, it's a very simple lab. What ideally should happen is the total work done on the system should be equal to the change in kinetic energy.